All right, continuing on with week 11 with dealing with vibration measuring instruments. We have another example from Inman. Don't know why that changed the page right now. Inman. And we have another accelerometer. Has a natural frequency of 120,000 hertz and a damping ratio of 0.2. We're going to find the error in the measurement of a sinusoidal thing that has a frequency of forcing frequency of 60,000. And I guess I could have just left them as kilohertz because we're gonna our next thing is to quickly find R of FF over FN. So that's going to be 0.5. We could do that in our heads. Or take 60 divided by 120, kept them in kilohertz, 0.5. Bunch of zeros, is that necessary? I don't know, probably not. And so we know that we have the z double dot over y double dot, and we're going to take 1 over the square root of, oh, I keep doing that. Why? Nobody knows. Squared plus 2 squiggle r squared. Getting boring with that colors. So plug in numbers in. 1 minus 0.5 squared whole thing squared plus 2 times 0.2 from here times 0.5 whole thing squared. So what we end up with is 1.288. So that's these two, but that means that our error is a whopping 28.8%. That is a poorly designed accelerometer. Should we continue on with the next problem? Because this one was so short at 2 minutes. Let's go for it, because that'll be the last one. Because I don't want to do this one, because I don't know the answer to it. So calculate the required damping factor. They don't give us enough information right in there. Determine the optimum range of the frequency range. I don't know. Over the widest possible range. I don't know how to do that problem. I forgot to ask him today. I saw him. I didn't ask him. I know it's stupid. I should have asked him. But anyway, let's start out here. We want to, this is the one we want to do, right? Sure. Design an accelerometer. Choose these parameters. Configured as in this guy right here for with a very small mass that can be accurate to 1% over the range right here, this frequency range. But you know what we're going to do, so we might as well just pick it. We know that we're going to go, let's select R is equal to 0.2. Anything over 0.2 doesn't make any sense. Anything below R, 0.2, I don't know why that would make any sense. And so at the frequency, at the FF, at the extreme right there, is 50 hertz. So if R is 0.2, we already wrote that down, Ted. All right, so we can have the Fn is going to be the FF divided by 0.2, or 50 divided by 0.2, and so we get 250. So I can't seem to write now over there. Getting tired. I got a lot of stuff to do tonight. What time is it? It's like 5:51. Eating dinner here at my desk again, away from my beautiful bride. Here's my omega n is going to be 2 pi times that Fn. So you could do math. 1,571 radians per second. We'll go through the charade again. We know we're just going to pick 0.7, so why are we doing this? I don't know. So the error now has to be between 0.99 and 1 over the square root of 1 minus r squared plus 2 squiggle r squared. And the other side of it, 0.01. Right? Can we do it? Yes, we can. Thank Bob Builder. Bob the Builder is one of my favorites. I love the Bob. My favorite Bob episode is when they save the hedgehogs. Are they porcupines? I can't remember. They build like a little tunnel underneath the road. I don't think Bob got the permits to do that. In my opinion. I don't think anybody would allow them to do it. But you want to have some serious silliness in your life? You want to look up this old comedy thing called The State. It was on MTV just as it started to go downhill. And they have something called the Porcupine Racetrack, and it was kind of funny to me. It was just as dumb as it could possibly be. Some Porcupine Racetrack. Fuck, that was long. Fuck. Anyway, you don't care. We should just look it up and put it onto this. I should put the link in. I should post the link on Blackboard. But anyway, we just went through this process right here. We went through the math to try to see what the range would be possible to be able to get these error terms. And guess what falls in that range? You guessed it. Select 0.7. So why did we even bother to do it? We could have just selected it and then chose it later. So now, by the way, we're going to do something in the design area that we said choose. You can pick a small, let's see, how small of a mass should we choose? Let's choose a mass of 0.01. That seems so random. Well, no. Is it good? Is it bad? I don't know. How much is that? It turns out if you look that up, do a little conversion on there, that's 0.353 ounces. That's very small. But it's like 10 grams. How much is a paperclip? How much does a paperclip weigh? I don't remember. Is it a gram? I think I'm supposed to remember that. Anyway, let's just go ahead and keep doing this. We're getting a little sleepy and sloppy. So the natural frequency is square root of kilogram. So if you know the natural frequency and the mass, you can get the stiffness. So at 0.01 and 1,571 squared, we get a stiffness of 24,674 newtons per meter. And if you don't like that value, choose a different mass. That's the kind of the design sort of thing that we're doing on here. We would like to not just randomly pick numbers, but it's not really quite random. We've already done some problems and saw that 0.1 doesn't sound all that crazy if you already have the math. Like you can see right here. Oh, there's the answer to that problem was 0.1516. Or in this one was given to you of 0.04. So we already have some quote unquote experience with this. So might as well pick one that we kind of like. And so we got that answer, and now we had what we selected the 0.7. So when we go for the CC, we know that's 2m omega n. So we already calculated that to be 2.01, and then we had 1,571, and that came out to 31.42 Newton seconds per meter. So when we go to our squiggle equals C over CC, we pick the C to be equal to squiggle times CC, or 0.7 times 31.42. So now we have a C of 21.99. And I ain't picking 24.99, I'm picking 22. So when we come to do our answers, we have M equal to 0.01, kilograms. We have a C equal to 22 Newton seconds per meter. And then we have a K. Might as well make it 25,000 because that sounds way better than the 3 sig figs. So boom, we have a design of an accelerometer that's going to fit into our requirements. And then, as I mentioned, I'm not doing this last example. It's not that I can't do it. It's just I haven't done it, and I want to mesh with what he has done. So I think all my examples are going to be good enough. So talk to you soon.